I welcome you all for this presentation. In this presentation, we are going to discuss about random bit generation and string ciphers. This is the overview of this presentation. There is introduction to random bit generation, then linear congruential generator, then blum shub generator, then ANSI X 9.17 pseudo random number generator, then string ciphers. Then we are going to discuss about RC4, then NREG model, health tests, then Intel digital random number generators. So in the last presentation, we have discussed about the random number generators. That is, we are having three types. That is, one is the true random number generator, then a pseudo random number generator, and the pseudo random function. Generally, the input to the true random number generator is the entropy source. Entropy source, in the sense, it is a value that is generated from the physical environment of a computer. And from that entropy source, a true random number generated is generated, and that true random number generator may be used as a seed or initial value for the pseudo random number generator. And using the pseudo random number generator with the help of the deterministic algorithm, we are generating a pseudo random number. And the difference between the pseudo random number generator and pseudo random function is that the pseudo random function always produces a fixed length bit of a random number, but this pseudo random number generator produces a open ended, that is any number of bits. It is of variable length. Random number is generated using a pseudo random number generator. That is the difference between pseudo random number generator as well as the pseudo random function. So here in this presentation, we are going to discuss about two important pseudo random number generators. One is the linear congruential generator. This linear congruential generator this algorithm is first proposed by Lechner, and it is parameterized with four numbers. That is m, the modulus, and the modulus always it is greater than 0. Next is a, the multiplier, and this a lies between 0 and m, and c is the increment, that is c lies between 0 less than or equal to z less than m, and x naught is the starting value or the seed value. And this seed value also lies between 0 and m, that is 0 less than or equal to x naught less than or equal to m. And the sequence of random numbers, this initially we are having the seed value, that is x naught. That seed value, how we are generating from the true random number generator only, we are generating the seed value, and we are using it in the linear congruential pseudo random number generator. Then we have to produce so many random numbers with the initial random seed value. So how we are producing the random number, sequence of random numbers in this sense, using this formula, we are computing or we are generating many sequence of random numbers, that is xn plus 1, that is we are having x naught value, so x1 we can generate, then x2, x3, likewise it goes on. So xn value we can generate a sequence of random numbers. So xn plus 1 equal to a xn plus c mod m. So using this formula, because this n plus 1, for generating the next sequence, you need the previous value. So in order to generate the x1 value, you need the XOR value. So x naught value. So x naught, you know, it is the initial set. So if we apply this x naught value, that is initial seed value, to this formula, we can easily get the pseudo random number, and we can generate the sequence of random numbers as well. So always we have to fix a number for this modulus, then multiplier as well as the increment. That is, if m, a, c and x naught are integers, then this technique will produce a sequence of integers with each integer in the range 0 less than or equal to xn less than n. The selection of values for a, c and m is critical in developing a good pseudo random number generator here. So the challenge in this linear congruential generator is fixing the value for the modulus, multiplier as well as the increment. And the x naught seed value, we know how to generate that seed value is generated using a true random number generator. So this is about the linear congruential generator. Next is Blum-Blum-Shub BBS generator. This is also a pseudo random number generator, and it has perhaps the strongest public proof of its cryptographic strength of any purpose-built algorithm. In the last presentation, we have discussed about the algorithm design. That is, in the algorithm design, we are having two categories of algorithm. One is the purpose-built algorithm, and another one is the cryptographic algorithm. So here, a purpose-built in the sense, this particular random number generator has to be, will be used to generate a sequence of random numbers for some specific purpose. So in such cases, we have to use the purpose-built algorithm. And this Blum-Blum-Shub generator, why the name Blum-Blum-Shub? In the sense, the name of the inventor. Blum-Blum-Shub is the name of the inventor. So they he invented this generator, and the name was given like this as Blum-Blum-Shub generator. So we can also generate any pseudo random number generator, and we can give our name for that generator also. So you can also try to generate any of the pseudo random number generator or any cryptographic algorithm, and you can give your name for that algorithm or the pseudo random number generator. Okay, next another technically this generator is named as cryptographically secure pseudo random bit generator. So based on the name of the inventor, this generator has got the name that Blum-Blum-Shub. Other name is technically, the name is cryptographically secure pseudo random bit generator, CP or BG. So this generator is defined as one that passes the next bit test if there is not a polynomial time algorithm that on input of the first k bits of an output sequence, that is, it can predict the k plus 1th bit with a probability significantly greater than 1/2. And the security of this BBS is based on the difficulty of factoring. That is, here how we are generating the pseudo random number means, first we have to select two large prime numbers, P and Q are the two large prime numbers we have to select. Then we have to, from the large prime numbers, we have to compute the n value. N means n equal to P into Q. So so difficulty in this algorithm is how to factor the value of n. So how we are using to, or how we are assuming that two prime numbers, that is P and Q. That is the difficulty in this algorithm. Then we have to assume a seed value also. S is the seed value. Let us see that detailed explanation in the next slide. So here you see, this is the algorithm to perform generate a pseudo random number using this Blum-Blum-Shub pseudo random bit generator. So here we are having n equal to P into Q. P and Q are large prime numbers. Then S is the seed value. So how we are generating is x naught equal to, x naught means the initial value equal to s square mod n. S also assumption, it is a seed value, s square mod n. Then for I equal to 1 to infinity, xi equal to xi by this what the whole square, that is the previous x value, the whole square mod n. Bi equal to xi mod 2. So suppose we have assumed that P equal to 383 and Q equal to 503. In that case, n equal to 192649. And the seed value we used is 101355. So using this value, if we are generating a pseudo random number, that is, if we apply this value to this algorithm, we are getting the value x0, x1, x2 up to x20. So likewise, we can generate a sequence of pseudo random numbers using the Blum-Blum-Shub algorithm. That is, here we are initializing these initialize with seed is, then we are generating x square mod n. So here the output is again given back to generate x square mod n. Then we are selecting the least significant bit, that is 0, 1. And always in the pseudo, whatever the pseudo random numbers we are generating, always we have to keep it in mind that the generated pseudo random number must satisfy two properties of the random numbers. What are the two properties? One is the randomness and another one is the unpredictability property. So those two properties has to be satisfied by whatever generated pseudo random numbers. Next is the pseudo random number generated using block cipher modes of operation. We have seen some modes of operation. So those modes of operation can also be used to generate the pseudo random number. So two approaches that use a block cipher to build a pseudo random number have gained widespread counter mode, and another one is the output feedback mode. We know what is a counter mode and what is the output feedback mode. Counter mode means there we are having a counter value, and parallelly each and every blocks are executing in this counter mode. So initial counter value alone we have to assume. Afterwards counter means increment of some value we have to give for other blocks and all. So initial first block value alone we have to finalize it, then we have to increment the value of the counter and we can use in for the coming subsequent blocks. So this counter mode, and this counter mode is recommended in NIST SP 890, that is ANSI standard X.82 and RFC 4086. And both this pseudo random number generated using block cipher modes of operation are given in RFC 4086. RFC, you know, in the first class we have discussed about RFC, that is request for comment. So those are standards. So these counter mode and output feedback mode can be used for generating a pseudo random number. And these are given in this RFC 4086. So this is the block schematic of how the counter mode is used to generate the pseudo random bits. So first it's given, one is given, then we are having the V. V generally it is a initial value or the counter value only, we are calling it as V. Then it is given to this plus operation we are giving. Then it is encrypted using any of the encryption algorithm, that V initial value is encrypted using any of the encryption algorithm with the help of the key K, and we are generating the pseudo random bits. Likewise here in the counter mode we are having a counter value. For that only increment, the increment operation is there. Plus in the sense it is a increment operator, that is the counter is incremented by one value. So V is the initial counter value, then it is incremented by 1. The counter value is incremented by 1 and the encryption process happens. In the output feedback mode, here we are having the initial value, that the seed value is there. Then we are performing the encryption. What do you mean by output feedback mode? The output of the encryption process is passed on to the next block. So in the output feedback mode, the output of the encryption process is only given to the next value, so that in the next block operates in the similar way. That is output feedback mode. So the difference between this output feedback mode and the counter mode is, here we are incrementing the seed value with the help of the counter value, that is incrementing with, plus 1, like that we are incrementing it. Then in the output feedback mode, the output of the encryption process is given to the next block. So this way we are generating a pseudo random bits using the counter as well as output feedback modes of operation. So this is an example how this pseudo random numbers are generated using the output feedback mode and the counter mode. See in this example, here they have find out the fraction of 1 bits, then fraction of bits that match with preceding block. They have find out, and the percentage, the fraction is 0.57, 0.51, 0.47. So we are getting different random numbers. Then the same thing, if you see the input seed value, the first value is same 1786F4 for the this one as well as output feedback mode, and for the counter they same only. From second onwards you see different values we are getting. So because here we are applying different modes of operation, so different random numbers are generated. For the same initial value we are getting different values for in the subsequent blocks in both the modes of operation, output feedback mode as well as the counter mode of operation. Next is ANSI X9.17, a pseudo-random number generator. Here this pseudo-random number is the strongest pseudo-random number generator and it is specified in ANSI. This is also a standard. ANSI X9.17 is a standard. And this pseudo-number generator, most of the applications, many applications are using this pseudo-random number generator in financial security applications and pretty good privacy. Here we are having the input, output as well as the key. So input, output, key, in the sense input, how we are giving us two pseudo-random inputs drive the generator. One is the 64-bit representation of the current date and time. The other is the 64-bit seed value. This is initialized to some arbitrary value and is updated during the generation process. That is the input. So input in the sense DTI as well as VI are the input. One is the seed value, another one is the date and time value. DT means date and time value. So how we are generating the value means using the date and time. Generally from the entropy source, if the input is from the entropy source, input we are passing it as an entropy source, then how we are generating the value based on the physical environment of a computer. So one of the physical environment is date and time. So using the date and time value, the input is generated. Another one is the seed value. One input from the physical environment, that is entropy source, and another one is the seed value that is passed here. Then the key, how the key is generated means the generator makes use of three triple dash encryption modules. All three makes use of the same pair of 56-bit keys which must be kept secret and are used only for this pseudo-random number generator. Likewise, the key is generated. So here we are having two keys K1 and K2. And then we are having the output. That is, the output consists of a 64-bit pseudo-random number and a 64-bit seed value. So 64 pseudo-random number Ri is the pseudo-random number and Vi plus 1 is the seed value. So in the encryption EDE, what do you mean by EDE? We are having triple dash we have applied, that is encryption, decryption, encryption process we have applied. That sequence we have applied triple dash, three triple dash. So 1, 2, 3, 3 triple dash operation is used in this ANSI X9.17 pseudo-random number generator. So the input to this is a date and time, that is entropy source, date and time. Then we are giving the seed value Vi. Then this two keys are also there, K1 and K2. Then we have used three triple dash with the sequence encryption, decryption, encryption, and we are getting a pseudo-random number as well as the seed value for the next generation. So this process is continued till as much as pseudo-random numbers are generated. This is about ANSI X9.17 pseudo-random number generator. Next is NIST, National Institutes of Standards and Technology counter mode. CTR means it is a counter mode deterministic random bit generator. Counter mode deterministic random bit generator. So this pseudo-random number generator is defined in NIST standard SB 890 based on the counter mode of operation, and this is widely implemented and is part of the hardware random number generator implemented on all recent Intel processor chips. Mostly in the hardware processors also this random number generator, we can generate random numbers using hardware also. So most of the hardware that is in Intel processor chips and all, this NIST CTR deterministic random bit generator is used, and this deterministic random bit generator assumes that an entropy source is available to provide random bits. That is, entropy, you know, is an information theory concept that measures unpredictability or randomness. And what the encryption algorithm we are using here is 3 desks with triple desks with 3 keys, or AES with key size of 128, 192 or 256 bits. So here, that is, out length is the output length, then key length, then seed length, then reseed interval. So for triple dash, what value they have used for out length, then key length, seed length and reseed interval. And for AES with 128 bit, AES with 192 bit and AES with 256. So these values are used in this NIST counter deterministic random bit generator. Let us see the schematic diagram of the CTR deterministic random bit generator. So this is the block schematic of the NIST CTR deterministic random bit generator. Here we are having the initialize and update function as well as the generate function. So first is the initialize and update function. In the initialize and update function, we are having a seed value. V is the seed value, that is the counter. Here counter is used, no? So counter, V is the counter, then key is the key K. So here it is incremented, +1. Always the counter is incremented. Likewise, we are iterating this process and we are getting a value. Then that is XORed with the entropy source. Then we are getting a key value as well as the V, the counter value we are getting. So this counter value is used in the next stage. Likewise, it goes on. Likewise, this is about initialize and update function. The next is generate. Once we have initialized the values and updated the function, then we have to generate the function in order to produce a pseudo random number. So here how it is happening means the initialize key and V value is given here. So that this V is a counter value, so it is incrementing and iteration is happening here. Then we are performing the encryption process and we are generating the pseudo random number using this NIST CTR deterministic random bit generator. So mainly this NIST CTR DRBG is used in the hardware, that is Intel processor chips and all are using this to generate a pseudo random number. Next is stream ciphers. We know how the stream cipher works. That is, we are passing a key K. That is the key is generated using a key stream generator. Then we are passing the plain text byte stream M, and we are XORing this plain text with the key K. Then we are getting a cipher text. See this example. The plain text is 11001100, and the key stream generated key is 0110110. Then we are performing the XOR operation. XOR operation, we know it is odd function. That is, if there is odd number of 1, then only it will be producing 1. Otherwise, it will be producing 0. So 0, 0, both 0. So 0, both 0, zeros, both 1, 0. So odd number of 1s means only we will be getting a 1 value. So we are getting the ciphertext like this: 101. 5 zeros we are getting. And how we are performing the decryption operation? The same key stream is used in the ciphertext, applied with the ciphertext, and the operation XOR is used. So if we are XORing, that is the ciphertext XOR with the key, we are getting the plain text. Whatever plain text available here, that we are getting here: 1100 1100. So this is the always the stream cipher works. Bit level operations are happen in the stream cipher. So this way only, this is the basic stream cipher. So this is the way how the stream cipher operates. So some of the design considerations for the stream cipher includes the encryption sequence should have a large period. Always the encryption sequence should have a large period. Say for example, that is, if a pseudo random number generator uses a function that produces a deterministic stream of bits that eventually repeats, the longer the period of repeat, the more difficult it will be to do the cryptanalysis. Why we are telling that, or the design consideration we are having in this stream cipher as the encryption sequence should have a large period means, so if we are having a large period, then only the cryptanalyst can't easily perform any attack, or the attacker or opponent can't easily extract or get the plaintext or the key. So that only we are having the large period. Next consideration is the key stream should approximate the properties of a true random number stream as close as possible. That is, there should be an approximately equal number of ones and zeros. That is, if the key stream is treated as a stream of bytes, then all of the 256 possible byte values should appear approximately equally often. And always what we have to do is, whatever random number we are generating, we have to always check that the randomness property hold uniform distribution as well as independence property. Uniform distribution in the sense approximately equal number of zeros and ones must be available. Independent in the sense each and every sequence must be independent to each other. But in order to verify the independent property, it is very difficult. So how we are verifying the independence property in the sense, we are performing some tests to check that it is not independent. Finally, we are telling that if we are proving that it is not independent, then we can easily tell whether it is independent or not. Likewise, only we are performing test or verifying the independence property. Next design consideration is a key length of at least 128 bits is desirable. Generally, we need a key length of at least 128 bits. That is, the output of the pseudo random number generator is conditioned on the value of the input key. The same consideration that apply to block ciphers are also valid here. Then, with a properly designed pseudo random number generator, a stream cipher can be as secure as a block cipher of comparable key length. That is, the main advantage is that the stream cipher that do not use this block ciphers as a building block are typically faster and use far less than the block ciphers. These are some of the design considerations of using the stream cipher. Next is RC4. It is a very important stream cipher. That is, it is designed in 1987 by Ron Drivers for RSA security. RSA means Driver Shamil Adi Ullman. In the coming chapters, we will be discussing that. So it consists of a variable key size stream cipher with byte-oriented operations, and it is based on the use of random permutation. That is, 8 to 16 machine operations are required per output byte, and the cipher can be expected to run very quickly in software. Here mainly, and where we are using RC4 in the sense it is used in secure sockets layer or transport layer security standards. These things, SSL, TLS and all, we will be discussing later. That is in 5th unit. And it is also used in wired equivalent privacy protocol and near Wi-Fi protected access protocol. Okay, so this RC4, it is a variable key size stream cipher with byte oriented operations. Mainly, this was designed to use it in the RSA, Ribose-Shamir-Adima. It is a very famous cryptographic technique. In that technique only this RC4 is used. Let us see the block schematic and operations of this RC4. Here, first we are having a state value. That is, state value has 0 to 255. That is 256 bytes are there. Then from that we are getting a key length. See here, first we have to perform initialization, initial state of S and T. T is a temporary variable. Already we discussed that it is a variable length. So temporary variable is there. So for I equal to 0 to 255, we are generating S of I. The state value we are generating S of I equal to I. So S of 0 equal to 0, S of 1 equal to 1, S of 2 equal to 2. Likewise, S of 255 equal to 255. Likewise, we are assigning. Then we are finding the temporary variable, that is T of I equal to K of I mod key length. So this is about the initialization. Then we have to perform initial permutation of S. That is initial permutation in the sense some transformation process or transposition process we are performing. How we are performing the transposition? That is, transposition is performed with respect to the temporary variable as well as the state value. So here we are performing some transposition. So the transposition is based on j equal to 0 for I equal to 0 to 255 do j equal to j plus S of I plus T of I mod 256. Then we are swapping S of I and S of j. So generally permutation in the sense we are changing the position of the value. So here we are performing some computation and we are doing some swap operation. That is, in order to make it a permuted one, we are making some swap operation. Finally, we are having the stream generation. How we are doing the stream generation is I equal to I plus 1 mod 256, then j equal to j plus S of I mod 26. Here also we are performing the swap operation, that is swap S of I comma S of j. Then we are getting T equal to S of I plus S of j mod 256. Then finally the K equal to S of T. So here in the RC4 what we are doing is just we are performing some permutation operation, that is some swapping operations. We are performing some computation, then we are performing the swapping operation. So in order to provide more security, we are giving this permutations operation. This is about RC4. Mainly this RC4 is used in RSA algorithm. While discussing RSA algorithm, let us see how RC4 is applied in RSA algorithm. So this is the strength of RC4. That is, many papers have been published analyzing the methods of attacking RC4. And none of these approaches is practical against RC4 with a reasonable key length. So what is the ultimate aim of all these cryptographic algorithms? In order to provide security, mainly in order to provide security only, we are having these cryptographic algorithms. And one more thing, we have to keep it in mind is whatever the algorithm we are designing for providing a security, always we have to think that the cryptanalyst can't perform any attacks. So he can't easily perform any attacks, because performing attacks or exploiting everything is possible, but it can't be done in a very easy manner. It must be practically unfeasible. In that sense only, we have to always design any cryptographic technique. So in this RC4 also, many papers were published, and now still also many papers are publishing. Many researchers are publishing the papers for attacking this RC4, but none of these approaches is practical against this RC4 with a reasonable key length. And another strength is, a more serious problem is that the web protocol intended to provide confidentiality on 802.11 wireless LAN network is vulnerable to a particular attack approach. That is, the problem is not with RC4 itself, but the way in which the keys are generated for users' input. And the problem does not appear to be relevant to other applications and can be remedied in web by changing the way in which keys are generated. Problem points out the difficulty in designing a secure system that involves both cryptographic functions and protocols and make use of them. So mainly, if we are applying or if we are using RC4 in our algorithm, we have to check, because here most of the things, whatever the initial value we are generating, it is a random number. Everything we are using, it is a random number. So the output or the percentage of security is based on the random number what we are using. So that only we have testing the random number to pass so many tests in order to provide a better security in whatever application that random number is used in. So these are the strengths of this RC4. Next is entropy sources. Here we are discussing in detail about the entropy sources. Already you know what is entropy source. A true random number generator uses a non-deterministic source to produce randomness. Most operate by measuring unpredictable natural process such as pulse detectors of ionizing radiation events, then gas discharge tubes and leaky capacitors. Mainly in Intel has developed a commercially available chip that samples thermal noise by amplifying the voltage measured across undriven resistors. Later on we will see one example of that pseudo-random number generator. Then Lava R&D is an open source project for creating truly random numbers using inexpensive cameras, open source code and inexpensive hardware. So the entropy source, that is the initial value, we can generate using the physical environment of a computer. That is many things, whatever the devices available or connected to the computer, we can use it, those devices or whatever the values generated by these devices or the time or clock, anything we can use it to use it as an entropy source. So possible sources of randomness include, in the RFC 4086 list the following possible sources of randomness that can be used on a computer to generate two true random sequences. That is, sound and video input also can be used, then disk drives also can be used to generate a true random number. There is an online service rand.org which depicts that how the sequences of random numbers are generated over the internet. So if time permits, you please go through that, what is random.org, and how the random numbers are generated using the sound or video input. In the sense, the input from a sound digitizer with no source plugged in or from a camera with a lens cap on is essentially a thermal noise. So mainly what we are discussing is in the Intel processors and all, mostly the pseudo random number generator is generated using the thermal noise. So the entropy source used is a thermal noise, and if the system has enough gain to detect anything, such input can provide reasonable high quality random bits. And from the disk drives also we can generate, that is, have small random fluctuations in their rotational speed due to chaotic air turbulence. The addition of low level disk seek time instrumentation produces a series of measurements that contain this randomness. So using these physical environment, we can generate a random number, and those generated random numbers must definitely satisfy the randomness condition. That is, what is the randomness condition? We are having two things. That is, always it has to satisfy the uniform distribution property. That is, approximately we must have equal number of zeros and ones. Another thing is independence property. So always you have to keep randomness means random bit generation means two characteristics you have to keep it in mind. That is randomness and unpredictability. Then coming to the randomness, always we have to keep it in mind that the uniform distribution is very, very important. Then independence property is also there. So comparisons of the pseudo random number generators and the true random number generators. So we have compared this PRNGs and TRNGs with respect to the efficiency, determinism and the periodicity. So the pseudo random number generator is very efficient and this true random number generator generally inefficient, because why this true random number generator is generally inefficient in the sense we are producing the seed value through the entropy sources and not seed value. The input to the true random number generator is the entropy source, but the so generally it is inefficient comparing to direct use of the random number generator using these true random number generators. But the value can be used as input to the pseudo random number generator, and we can generate some other pseudo random number, so that it is very efficient. And coming to the determinism property, it is very deterministic under PRNGs and non-deterministic under TRNGs. Coming to the periodicity property, the pseudo random number generator is periodic and this is aperiodic TRNGs. So another thing is conditioning. Conditioning means in the true random number generator may produce an output that is biased in some way. That is biased in the sense such as having more ones than zeros or vice versa. So we have seen that true random number generator is inefficient. Like in the previous slide we have discussed that it is inefficient. Why inefficient? In the sense the randomness property is not, it is not holding full randomness property, so that only we are calling it as inefficient. That is, it is biased to some values. That is, sometimes it is biased to ones and sometimes it is biased to zeros. That NIST SP 890B defines a random process as biased with respect to an assumed discrete set of potential outputs if some of those outputs have a greater probability of occurring than do others. Then the entropy rate, another term, entropy rate. This NIST 890B defines the entropy rate as the rate at which the digitized noise source provides entropy, and it is a measure of randomness or unpredictability of a bit stream, will be a value between 0, no entropy, and 1, full entropy. And for that we are having the algorithms, conditioning algorithms and de-skewing algorithms. Conditioning algorithm means it's a method of modifying bit stream to further randomize the bit. Generally, we used to apply shampoo in our hair, but later sometime, because earlier and all only shampoo is available, but later on, but you people may aware from the small stage itself, I think so. So, but earlier and all only shampoo alone is available. Afterwards, only conditioner came. So likewise, what is the purpose of conditioner? In order to condition the hair in an effective manner, for that only we are having a conditioner with the shampoo. So, so they given shampoo, then we have to apply conditioner, or in some brands and all, conditioner is given along with the shampoo, so that many things are happening. So in order to provide a better thing, only we are having a conditioner. So likewise only here also in random bit generation also we are generating a random number, you see, true random number generator, but there may be some biases in the generated random number. So what we are going to do, we are just conditioning the random number. That is, for that only we are having the conditioning algorithms. So it is a method of, here we are just modifying the whatever bit stream generated to further randomize the bits. So in order to provide more randomness to the generated random number, we are going in for this conditioning. And typically conditioning is done by using a cryptographic algorithm to scramble the bits so as to eliminate bias and increase the entropy. So the two most common approaches are, we will be discussing the approaches, that is hash function, that we are discussing the conditioning functions we are going to discuss in the coming slides. So what is the purpose of conditioning is to provide more randomness to the generated random number. For that only we are going in for this conditioning. So first conditioning thing is hash function. So the detailed explanation of this hash function we will be discussing later, because we are having a separate unit for that. So this hash function produces an n-bit output from an input of arbitrary length. A small simple way to use a hash function for conditioning is as follows. So this is the procedure to condition the generated random number. That is, blocks of m input bits with m greater than or equal to n are passed to the hash function, and the n output bits are used as random bits. Then to generate a stream of random bits, successive input blocks pass to the hash function to produce successive hashed output blocks. Another one is the non-deterministic random bit generator. So in the non-deterministic random bit generator, what we are generating is, we are having a non-deterministic bit source, that is noise source is given to the digitization, and the result of digitization is given to the health testing. Why we are going in for health testing? Generally, if we are not feeling well, we will go in for the hospital. So in order to test the health condition of ours. So likewise, we are also testing the health condition of the generated random number, whether it is truly random, or what percentage of severity in the randomness is available, whether it is very low, high, medium, like that. In order to test the condition of the random number, we are going in for this health testing. Then we are having a conditioning process. Then the result of conditioning is again given to the health testing. So first, whatever thing is generated, we are going in for the health testing. Then after conditioning, before conditioning, what is the status, and after conditioning, what is the status, that we are checking. So let us see some of the health testing methods. Health tests on the noise source. The nature of the health testing of the noise source depends strongly on the technology used to produce the noise. Generally, the assumption can be made that the digitized output of the noise source will exhibit some bias. That is, traditional statistical tests are not useful for monitoring the noise source, because the noise source is likely to always fail. And the tests on the noise source need to be tailored to the expected statistical behavior of the correctly operating noise source. So what we are expecting is, we have to determine whether the generated random number is providing all the characteristics, that is randomness and unpredictability property. So the entropy source from the noise source, if you are generating some random numbers, then we are testing whether it is providing whether it is a good random number or not. Likewise, we are just testing, that is bias is there or not, that we are testing in this random number. So for this also we are having a standard, that is SB890B specifies that continuous tests to be done on digitized samples obtained from the noise source. The purpose is to test for variability and to determine if the noise source is producing at the expected entropy rate. And two tests are there always. If you are generating a random number using true random number generator, that number has to be passed on to these two tests, that is repetition count test and adaptive proportion test. Repetition count test means designed to quickly detect a catastrophic failure that causes the noise source to become stuck on a single output value for a long time, and it involves looking for consecutive identical samples. Next is the adaptive proportion test, that it is designed to detect a large loss of entropy such as might occur as a result of some physical failure or environmental change affecting the noise source. So these tests has to be done for the number generated using, that is the entropy source used from the noise source. So here this is gist of that. That is SB890B specifies that health test should also be applied to the output of the conditioning component, but does not indicate which test to use. Because we are having two tests, so it doesn't mention that what test is to be used here. Then the purpose of the health test on the conditioning component is to assure that the output behaves as a true random bit stream. It is reasonable to use the test for randomness defined in SP 822. So all these things are related. So many standards are there for checking the randomness, checking the unpredictability. Many standards are there. So all these things are related. That is SP 890B. There we are using that. We have to check this SP 820. That is, after performing the test, we have to check whether the randomness is provided or not. So we know that this true random number generator is inefficient compared to pseudo random number generator. So what we are doing is, we have to, after generating number, we are performing some conditioning operation. Conditioning operation means we are again making the number to making as a good random number. That is re-randomizing the random number generator. Then we are giving that number to for some health test. Health test means whether the bias is eliminated or not, or whether the given number is providing a true randomness or not. Likewise, we are in order to check those things, we are going in for this health test. So lastly, we are going to discuss about this Intel digital random number generator. That is, we already seen that this random number generator are used in this Intel processor chips. So how it is used here, let us see. So true random number generators have traditionally been used only for key generation and other applications where only a small number of random bits were required. So mainly true random number generator is used in such cases. This is because true random number generators have generally been inefficient with a low bit rate of random bit production, because more biases are there in this true random number generator. So only in these cases alone we are using this true random number generator. So the first commercially available true random number generator that achieves bit production rates comparable with that of PRNGs is the Intel digital random number generator, offered on a new multi-core chip since May 2012. It is implemented entirely in hardware. The entire digital random number generator is on the same multi-core chip as the processors. So this is the architecture of the Intel digital random number generator. So here we are having the digital random number generator. Here the input is the entropy, hardware entropy source. Then what we are applying is AES, CBC, cipher block chaining, MAC, message authentication code based conditioner we are applying. Then it is passed on to the hardware, that is AES, counter based digital random bit generator. Then we are passing to the CENRNG. And we are passing it to the reseed instruction in each and every core, because here multi cores are available. So this hardware is passed to this reseed instruction, and this hardware, that is AES CTR based DRB and VG, is passed to the RD random instruction. Here in this hardware entropy source, we are having inverters. That is, inverter is there. So you know, inverter means it changes from zeros to ones and ones to zeros. Let us see the logical structure of this Intel digital random number generator. So this is the logical structure of the Intel digital random number generator. I already told you that in the hardware entropy source we are having a inverter. So inverter just converts zeros to ones and ones to zeros. Then that is passed on to this AES CBC MAC based conditioner, and the result of that is passed to AES counter based pseudo random number generator. So here the encryption operation is performed. So whatever the value we are getting from the hardware entropy source, that is divided into 128 bits, 28 bits. The input to each and every encryption process is of 128 bits, then key is given. Encryption operation is performed. Here encryption is performed based on advanced encryption standard. And here cipher block chaining is used. The result of the encryption is passed to the next block. Cipher block chaining mode of operation is applied here. Then here is AES counter based pseudo random number generator is used. That is, here counter mode operation is performed. See here increment of 1. So here counter is used. Then here also the encryption operation used is advanced encryption standard only. Finally, we are getting the pseudo random number. So this is fully based on the hardware. So hardware means it provides compared to software, the random numbers are produced in a fast manner in this hardware Intel digital random number generator. So in this presentation, we have discussed about random bit generation. So that is two main algorithms, linear congruential generator and Blum-Blum-Shub generator. Then one standard we have discussed for a pseudo-random number generator, that is ANSI X 9.17. Then we have discussed about the stream CIFOs, that is RC4. Then NREG model. Then we have discussed about how to condition the generated random number, that is providing more biases. Then what is a health test for this random numbers? Finally, this random number generators are used in this Intel processor chip. So we have seen random number generator using this Intel digital random number generator. So this whatever discussed so far is available in chapter 8 in your William Stallings textbooks. You please go through that. Thank you.